Have you ever picked up an old, really well-loved library book, maybe like an old science textbook, and noticed that the very first pages, they're often way more worn, more dog-eared, maybe a bit faded compared to the ones near the back?
Oh, definitely, especially those old reference books.
Right. It's a funny little detail, isn't it? Well, turns out, if that book happened to be a table of logarithms, that seemingly, well, mundane observation, it actually pointed to something pretty profound.
Ah, you're talking about that hidden mathematical pattern.
Exactly. It permeates our world from like how rivers flow to stars twinkling way out there. We're talking about Benford's law.
And it's not just some quirky thing, is it? It's like a fundamental property of how numbers often scale in the real world.
Yeah, suggesting that in naturally occurring data sets, the digit 1 shows up as the first digit way more often than any other number, which is kind of weird when you first hear it.
It really is fascinating because it reveals this surprising underlying order in stuff that might just seem like random data.
So today, we're going to try and uncover this mathematical curiosity. We'll look at its history, where it came from.
And then dive into its vast and sometimes really unexpected applications. You mentioned fraud detection, but also cosmology.
Right. And then, importantly, we need to talk about the intriguing challenges it faces, especially with some of the super advanced astronomical data we're getting now, like from Gaia.
Mm-hmm. It's not always straightforward.
So this deep dive is based on, well, a stack of really captivating sources, research papers, detailed notes, the works. So let's jump in.
Do it.
Okay, so this whole story, this like incredible insight, it actually starts with an astronomer mathematician, American guy named Simon Newcomb.
Back in 1881, right?
Yeah, 1881. He was the first one to notice this peculiar wear pattern on his log tables. But it wasn't just his books. He realized the leading digits in collections of numbers weren't, uniformly distributed.
He saw that 1 was the most common, and then it sort of dropped off steadily down to 9. What's fascinating here is, like you said, how such a practical, almost everyday observation, the wear on a book, could actually lead to a profound mathematical principle.
He put it pretty clearly, too, didn't he? Noticed how much faster the first pages wore out.
Yeah, he specifically said the first significant figure is 1 more often than any other, and the frequency drops as you go up. Simple observation, deep implications.
And Newcomb himself, well, he was quite the figure. I mean, professor of maths in the U.S. Navy and Johns Hopkins.
Oh, yeah, director of the Nautical Almanac Office.
Yeah.
His work on planetary motion, astronomical constants, speed of light.
Even the Earth's wobble, the Chandler wobble. Just an astonishing range of expertise.
Surely, but, despite him discovering it first.
It gets called Benford's law.
Right, because Frank Benford rediscovered it, basically, in 1938.
Okay, let's unpack this then. How does this law actually work, beyond just noticing worn pages?
Well, the way Newcomb originally formulated it, specifically for that first significant digit, is that the probability, PD, of seeing a leading digit D is log base 10 of D plus 1 minus log base 10 of D.
Okay, logs. For those of us not doing maths every day, what's the gist?
Fair enough. Think of it less about the calculation itself and more about how numbers tend to grow in the real world. Lots of natural things don't just add up linearly, right? They grow multiplicatively.
Like compound interest. Or population growth.
Exactly. And when things grow like that multiplicatively, you sort of spend more time, numerically speaking, in the lower numbers, the 1s, 2s, 3s, before you jump to the next order of magnitude, the next power of 10.
Ah, okay. So that's why you see ones so much more often, because things hang out in the 100s or 1000s longer than the 900s or 9000s.
That's the intuitive idea, yeah. And the math bears it out. It leads to this really skewed distribution. Like the digit 1 appears as the first digit in about 30.1% of cases.
30%, that's huge.
It is. And then compare that to 9 emits, which only shows up about 4.6% of the time you see that big drop-off.
Wow.
And the law tends to be most accurate when your data set, your numbers, are spread across many orders of magnitude. You need that big scale.
Does it relate to other weird math patterns?
It does, actually. There are parallels with Zipf's law. You see that in linguistics, like with word frequencies.
Oh, right, where words like the and a are super common and most words are really rare.
Exactly. It's another one of those non-uniform sort of power law distributions that just pop up everywhere in language and nature.
So Benford, the guy who got the name, he didn't just take Newcomb's word for it, right? He actually tested this stuff.
Oh, extensively. He wasn't just theorizing. He went out and gathered tons of empirical data. I mean, the list is amazing.
What kind of things?
Surface areas of 335 rivers, population sizes of over 3,000 U.S. communities, 104 physical constants, 1,800 molecular weights.
Even looked at street addresses, didn't he?
He did. It's incredible. He just grabbed anything he could find that had numbers spanning large scales and checked if they fit the pattern.
That's some serious dedication to an observation.
And it goes further into physics, too. It shows up in complex atomic spectra, the energy spread of subatomic particles, hadrons, even the half-lives of radioactive elements.
So it's not just like accounting numbers or populations, it's
Yeah.
in fundamental physics too.
And for a really precise example, look at powers of 2. 2, 4, 8, 16, 32.
Okay.
If you look at the first billion powers of 2, the number starting with the digit 1 is exactly 301,029,995.
Whoa. Okay, and what does Benford's law predict?
It predicts 301,029,995.66.
That is incredibly close, like astonishingly close.
It really is. Shows the precision in certain mathematical contexts.
Okay, here's where it gets really interesting for, practical stuff. Because this law is so reliable for natural data, people use it to catch cheats, right?
That's one of its most famous applications, yeah. It's a powerful tool.
How so? Like, how does knowing one is common help find fraud?
Well, think about it. If you're trying to fake a bunch of numbers, say, in accounting books, or maybe expense reports, or even election results.
You probably wouldn't think to make more numbers start with 1 than 9, right? You try to make them look random, maybe more evenly spread.
Exactly. People fabricating data often fail to replicate this natural Benford distribution. Their made-up numbers tend to have too many high starting digits, or just look too uniform. That deviation from Benford's law is a big red flag.
So it's used in audits, tax investigations.
Yep, forensic accounting, tax return analysis, sometimes even looking for voter fraud patterns, or checking if digital images have been messed with, because manipulated data often sticks out like a sore thumb when you check the first digits.
If we connect this to the bigger picture then, it's like this simple mathematical pattern is an underlying truth for so much stuff, natural or man-made, that you can use it to spot when something's off.
Precisely. It becomes a really useful tool for anomaly detection across all sorts of different fields. It's quite remarkable.
Absolutely. Okay, so finance fraud. What about way out there? Let's turn our gaze to the cosmos. Does Benford's law hold up in the vastness of space?
It's definitely been looked at. Alexopoulos and Leontinas, back in 2014, they were some of the first to really apply it systematically to astronomical distances.
And what did they find? Galaxies, stars.
They found that galaxy distances followed the law reasonably well, was their phrasing, but star distances followed it very well. And interestingly, not just the first digit, but even the second and third significant digits for stars showed good agreement.
Very well for stars. Is there a reason why galaxies might follow it, a theoretical basis?
There is, actually. Hill and Fox, a couple of years later in 2016, they connected Benford's law directly to Hubble's law.
Hubble's law, the one that says galaxies further away are receding faster?
That's the one. They argued that the relationship described by Hubble's law naturally leads to galaxy distances following Benford's law. They even suggested it could be seen as, quote, independent evidence of the validity of Hubble's law.
Wow, okay. That's a pretty strong claim, connecting this weird number pattern to fundamental cosmology.
It is. It shows how deep these patterns might run.
Fascinating. Okay, what about smaller scales? Planets, maybe, like the ones Kepler found.
Yeah, people have looked at exoplanets, too. Some properties of the Kepler planets, things like their mass, the size of their orbit, the semi-major axis, how long their year is, orbital period, those seem to follow the Benford distribution reasonably well.
Okay, some properties. What about others?
Well, interestingly, planet radii, how big the planets actually are, they seem to fail to follow the law. That's a key finding.
So mass, orbit size, period, yes. Radius, no. That's intriguing.
It is. And it's not the only astronomical data set that fails. Mamidipaka and Desai just last year found that pulsar dispersion measures.
Dispersion measures. That tells you how much space gunk the signal traveled through, kind of related to distance?
Sort of, yeah. It's related to the integrated electron density along the line of sight. They found that those measures for pulsars, and also for fast radio bursts, they also failed to follow Benford's law.
So it works sometimes in space, sometimes not. Why the difference? Why planet radii or pulsar measures? Why do they just not fit?
That's an excellent question. And it really underscores that Benford's law isn't like a universal magic wand for every single data set. The underlying physical distribution of the things you're measuring really matters.
It needs that spread across many orders of magnitude, and maybe some processes just don't generate numbers that way.
Exactly. Or maybe the way we measure them or selection affects what we're able to see, influences the distribution we end up analyzing. It reminds us to be careful about where we expect it to apply.
Which brings us neatly to this really interesting puzzle with data from the Gaia mission, the ESA satellite mapping, like billions of stars with insane precision.
Gaia is a game changer.
So going back to those earlier studies like Alexopoulos and Leoncinus in 2014, they used the HYG database, about 115,000 stars, and found good Benford agreement for distances, right? First, second, third digits even.
Already good fit.
But then Gaia comes along, Gaia DR2, the second data release. And de Jong and others, in 2020, they looked at the parallaxes from Gaia, 1.3 billion of them.
A huge data set. And the precision is incredible. Parallax is that tiny angle shift we measure.
And what did they find with those parallaxes?
They found something striking. The parallaxes themselves follow Benford's law even closer than the older distance estimates did. Like, stars with a parallax starting with 1 are 5 times more numerous than those starting with 9.
5 times. Okay, so the raw measurements, the parallaxes from Gaia, fit Benford's law beautifully, super closely.
Exactly, a real testament to the data quality and the sheer number of stars.
And here's the core puzzle, right? Despite the parallaxes following the law so well, the stellar distances you calculate from those exact same parallaxes, they do not follow Benford's law.
That's the crux of it. The measurement follows the law, the derived physical quantity doesn't.
So what does this all mean? Why would the angle measurement fit, but the distance calculated from it not fit?
This raises a really important question, actually, about how measurement techniques, error propagation, and mathematical transformations affect these kinds of statistical properties.
Okay.
The issue comes down to how you get distance from parallax. Fundamentally, distance is 1 over parallax, 1p. But when you have even a small uncertainty, a small error in measuring that tiny parallax angle...
Which you always do, right? Nothing's perfectly measured.
Nothing's perfect. And especially for distant stars where the parallax angle is incredibly tiny, even a small percentage error in the parallax measurement becomes a big problem when you just flip it, when you take the reciprocal to get distance.
How so?
Because a nice symmetrical error distribution in your parallax measurement, it's equally likely you measured it a tiny bit too high or a tiny bit too low that transforms into a very asymmetrical probability distribution for the distance.
Ah, okay. So the error bars on the distance aren't even on both sides.
Exactly. Especially when the relative parallax error gets above, say, 10 or 20%. Just taking 1p gives you a biased suboptimal distance estimate. Your uncertainty balloons out unevenly.
You used the slingshot analogy before we started recording, like trying to hit a target far away.
Yeah, that's a great way to think about it. If you're close, a tiny wobble in your aim doesn't matter much.
No.
But from miles away, that same tiny wobble means you could miss by a huge amount. And probably more likely to miss long than short, maybe. It's similar here. The small symmetric parallax uncertainty becomes a big, skewed distance uncertainty.
Okay, so just taking one parallax is tricky for many Gaia stars. What do researchers do instead?
They use more sophisticated methods, often Bayesian approaches, where they incorporate prior assumptions about the galaxy, like how stars are generally distributed, or they bring in extra data, like the star's brightness and color from photometry, to help constrain the distance estimate.
People like Baylor-Jones, Lurie, Anders, they've developed these better distance catalogs.
Right. But even using these improved, more statistically robust distance estimates, the overall distribution of stellar distances derived from Gaia still doesn't really follow Benford's law in the simple way the parallaxes do.
And there were predictions about this, weren't there? That the distances wouldn't follow the law.
Yes, exactly. Realistic simulations of the galaxy, like those by Robin and collaborators back in 2012, actually predicted that the true distances wouldn't be expected to follow Benford's law.
Why not? What's going on in the galaxy itself?
It's basically down to a combination of two things. The Milky Way's luminosity function, which is just, the mix of intrinsically faint and bright stars that exist, and Gaia's selection function, basically, which stars Gaia is most likely to actually see and measure well.
Okay.
The combination of those results in Gaia seeing a kind of bimodal distribution of stars.
Bimodal, meaning like two main groups.
Yeah, essentially. You've got a big group of relatively nearby fainter stars, like dwarfs in our local neighborhood. And then you've got another group of very distant, intrinsically very bright stars, like giants, maybe towards the galactic center or in the spiral arms.
So it's not one smooth distribution of stars stretching out. It's more like clumps.
Sort of. You have these concentrations at different distance scales because of the mix of star types and what Gaia can see. And that complex bimodal distribution just doesn't fit the simple single peak at low digits pattern that Benford's law describes.
So the key takeaway here, the really intriguing bit from de Jong et al.'s work, is that the Gaia parallaxes, the measurements, follow Benford's law remarkably well. But the true distances derived from them, even with clever methods, probably do not, because the galaxy itself isn't structured that way.
That's the nub of it. It's a subtle but really crucial distinction. It highlights this complex interplay between our observations, the maths we use to interpret them, and the actual underlying physical structure of the universe.
It's a fantastic example of how you can have these incredibly precise measurements that follow a statistical law, but the physical reality they point to might have a different structure entirely, partly because of how the universe is, and partly because of how our instruments see it.
Couldn't have said it better myself. It's a deep point about measurement and reality.
You know, this whole story of Benford's law, from Newcomb seeing worn pages, to Benford testing rivers, to us now puzzling over Gaia data, it really highlights the winding path of scientific discovery.
Absolutely. It's rarely a straight line.
And speaking of how discoveries get made, and maybe more importantly, how they get named, there's that fascinating law that perfectly captures the irony here, Stigler's law of eponymy.
Ah, yes, Stigler's law, my favorite meta law.
Which states, basically, that no scientific discovery is named after its original discoverer. And Benford's law, which we now know, was really first described by Simon Newcomb. Well, it's a textbook example.
It really is. And it's almost funny how often this happens, especially in astronomy. You see it everywhere once you start looking.
Like Bode's law for planet spacing. That wasn't Bode first, was it?
Nope, that was Johann Titius. Or the Cassegrain telescope design reflecting light back through a hole in the main mirror, known to Cavalieri and Mersenne before Cassegrain.
Dyson spheres, those giant structures around stars.
Credited by Freeman Dyson himself to the sci-fi writer Olaf Stapledon.
Okay, keep going. This is fun.
The Fermi paradox, where is everybody? Regarding aliens. Konstantin Tsiolkovsky talked about that decades before Fermi. The Gaussian distribution, the bell curve.
Not Gauss.
Introduced by Abraham de Moivre. Halley's Comet. Seen for centuries, millennia even, before Halley calculated its orbit. Hubble's law.
Let me guess. Lemaitre.
Georges Lemaitre, exactly. Derived the expansion theoretically before Hubble observed it. Captain's star, cataloged earlier by Gould. The Oort cloud of comets, postulated first by Ernst Knoppik. Olbers' paradox, where the night sky is dark.
Kepler.
Kepler wondered about it centuries before Olbers. The list just goes on and on.
It's amazing. And the best part, the real kicker about Stigler's law?
Is Stigler himself. In naming the law, Stephen Stigler credited sociologist Robert K. Merton as its discoverer.
So he proved his own law by following it when naming it.
It's just perfect. A wonderfully self-referential, slightly absurd piece of scientific history.
It really is.
Yeah.
Okay, to bring us full circle, back to Simon Newcomb, the actual first observer of what we call Benford's law, I want to share two quotes from him because they show this incredible shift in his own perspective on science, on astronomy.
Oh, interesting.
In 1888, he wrote something pretty definitive. We are probably nearing the limit of all we can know about astronomy.
Wow. Famous last words, eh? Given what happened in the 20th century.
Right, but then fast forward to 1903, near the end of his life, his view had changed completely. He wrote, "What lies before us is an illimitable field.
Illimitable. Limitless.
The existence of which was scarcely suspected 10 years ago, the exploration of which may well absorb the activities, for as many generations as were required to bring electrical science to its present state."
That's a profound shift from thinking we're almost done to seeing endless frontiers opening up.
Exactly. So from the worn pages of an old log table all the way out to the structure of the cosmos revealed by Gaia, we've taken quite a deep dive into Benford's law today.
We really have. We've seen how this peculiar mathematical pattern, first spotted by Newcomb, then nailed down by Benford, gives us these surprising insights into, well, everything from dodgy accounting to the properties of distant galaxies.
And we've also bumped up against its limits, right? Uncovered those nuanced challenges, especially when you apply it to really complex, modern astronomical data like Gaia's.
Yeah, it's a powerful reminder, isn't it? That even seemingly simple laws, simple rules about numbers, can reveal profound complexities when you push them against the messy reality of the universe and our cutting-edge observations.
Those aha moments, though,
Yeah.
understanding that simple rule about first digits can really open doors, help you see these deep structures in data, maybe even in the universe itself.
Absolutely. And thinking about Newcomb's incredible change of heart, going from believing we were nearing the limit to seeing an illimitable field.
Yeah.
Maybe consider how the applicability and sometimes even the failure of laws like Benford's in these new contexts, like with Gaia's distances, how that serves as constant evidence that we are absolutely still exploring those illimitable fields. We're far from done.
That's a great point. The exceptions are just as interesting as the rule sometimes. So here's a final thought for you to mull over. What other simple, maybe hidden underlying patterns might still be out there, holding profound, undiscovered insights about the world right around you?
Something to keep an eye out for.
Definitely. Something to ponder until our next deep dive.